Good morning, everybody. I'm very happy to have the chance to talk about UV disinfection in this session again. And my today's topic is to illustrate why UV is a good alternative over chlorine and what design approaches are there available today in order to give you the confidence that it's working as it should. So this is an overview of my today's presentation. I will talk a little bit about the chlorine-related hazards which actually lead to a shift to UV and other alternative disinfection technologies. Then what is UV and how we today size and design UV systems for wastewater disinfection. Then talk a little bit about control strategies which allow you for nearly unattended automatic operation, and then conclude. So actually looking back when disinfection came up, that was like more than 100 years ago. There were a lot of diseases related to waterborne pathogenic bacteria. And when chlorination was used on the waters, these infections dropped significantly. And that's when chlorine was invented and established for disinfection processes. And it has not really changed over the past 100 years. And nowadays, people are a lot more concerned about the downsides of chlorine. I mean, initially it was a good thing because public health could be protected by the use of it, but now people are getting more and more concerned about the hazards which are related to chlorine. And here is an overview about what people are concerned of. First of all, chlorine is a toxic gas, so if there are some leakages, it really can be dangerous for the people working with it. And then another main concern is the formation of disinfection byproducts, which are typically carcinogenic and which are also difficult to destroy then in the further treatment chain. It is explosive, especially in warm climates. You need to have proper cooling of the tank so that nothing is happening. And also for the transport, this all needs to be taken care of. And if you actually count all these safety measures in, chlorine is not actually as cheap as it is perceived in the first place. Then another major shift away from chlorine was actually started when it was found that it's more or less ineffective against parasites like crypto and giardia. That was the time when, for instance, the US were shifting completely away from chlorine to UV for drinking water. And that was also the time where a very extensive guidance manual on UV system design was established in order to make it a real safe alternative. And last but not least, it's a very corrosive agent. So you need to be aware of that when designing all the piping and all the distribution services. So, and then there are a few specific points I would like to highlight when it comes to disinfection of wastewater. So here we typically have particularly high TOC levels, and that actually enhances the formation of those undesired disinfection byproducts. And additionally, you need to also dose quite a bit of chlorine because it's just oxidizing whatever there is in the water. And if you do have a lot of organic matter, you also need to dose high levels of chlorine. Then, on the other hand, as it is observed that it is very dangerous also to the aquatic life, and if you have some sensitive wetlands or fishing areas, then you may want to reduce the residual content before you discharge the wastewater into your receiving water bodies. So this also becomes more and more regulated. And I've seen that here, even for South Africa, there is also a guideline that you should discharge 0 chlorine, at least for some special waters. So this would mean that you need to have a dechlorination step after you chlorinate it, which again adds to the cost of chlorine dosing. And if we look at water reuse, which is, as far as I heard over the last days, and more and more important topic here for this area, it's also probably not the best choice to add chlorine for disinfection, because if it's used for irrigation, you may have the salts generated on the soil. Yeah, so there will be an increase of salt level over the time if you continue to use chlorinated water reuse for that purpose. So if you look at the different alternatives which are there available, I'm here looking at the chlorine, chloramines, ozone, chlorine dioxide, and UV. So these are actually the main downsides of chlorine. And if you look at all the other technologies, you will find that UV is pretty good at every of the considered parameters. And moreover, it's not a very complex technology, but straightforward and simple and relying purely on physical processes. Because it's actually the UV lamps which are emitting wavelengths of 254 nanometers, which are absorbed by the microorganisms. The DNA is destroyed, so they cannot replicate, and they are not infectious anymore. So that's as simple as UV works. So in summarizing, looking at chlorine and UV, you find that all the downsides of chlorine are actually not occurring if you use UV instead. But I can understand that there, especially if you want to use a new technology which is not so well known in a region, you want to be sure that it's doing what you expect it to do. And that was also the driver that different organizations came together in order to understand what is today's best approach to design UV systems. And they actually developed a number of guidelines, which I will talk about in a few seconds. But before that, I would like to share the historic approach, how UV systems were designed in the past, especially for wastewater. That was a purely mathematical approach where you assumed basically the reactor's geometry, the lamp properties, and by that calculated the retention time and the intensity which is delivered by the UV lamps installed, and then you were coming to a UV dose. So that was a purely mathematical approach, assuming a number of ideal conditions and not considering actually the water's properties or the microbiology properties. And there are quite some differences. So, with this diagram, I would like to illustrate the shortcomings of it. So in this case, we have two different reactors, and one has a lot of lamps which are not so powerful, and the other one, a few very powerful ones. And I think the two are actually delivering, based on this calculated dose approach, the same dose. Yeah, 40 millijoule here and 40 millijoule there. But I think it's quite obvious that in reality, this reactor will deliver a much better disinfection performance because dose is distributed a lot more evenly than this one. Yeah, because if you imagine that there's 1% of flow passing through on this end with not getting a lot of UV dose, it will not get the disinfection desired. So they will not deliver the same disinfection result. And the operator actually, he doesn't care about a dose. Yeah, he just wants to see that he's meeting the permit requirements, that you get the log reduction you expected it to. So therefore, it's so important how effective the UV systems are designed. And with today's computational fluid dynamics, we can already in the development phase of a new reactor, determine how well UV dose is distributed within the reactor. I mean, we are still not in the ideal situation, but it's getting closer to this ideal situation with every new invention. And here you see a comparison of two systems, and you see that in this reactor system, the dose distribution is fairly even. Yeah, the colors are about the same, whereas here, the dose distribution is a lot varied, yeah, with very weak areas here in these areas and very strong areas here in the middle between the lamps. And actually, it is, in order to achieve the best performance possible, a very uniform dose distribution is desired. And then on the other hand, it was also found that different pathogens exhibit different dose response behavior. So therefore, it is important to always associate to the dose to a certain organism. Yeah, because there are some which are very sensitive to UV light, yeah, which are also all the coliforms. And then there are others which are a lot harder to destroy. And we today have the technologies to understand how sensitive an organism is, even from a specific water sample, and to design the UV system accordingly. Yeah, for instance, here Cryptosporidium and Giardia, they have a very low resistance. That means that already a very small UV dose is sufficient to achieve a 3 or 4 log reduction of these types of pathogens. And then if we look more to the right, it becomes more difficult, but especially E. coli, they are also very easily to be destroyed, and that's very often an important indicator organism in wastewater. And yeah, with collimated beam tests, you can also establish the site-specific behavior. So not only considering the different types of organisms, but also even looking at the site-specific behavior. And in the past, this has only been done by piloting on site. Yeah, and now we can assess with a fairly simple collimated beam test how the dose response behavior of a water is and the pathogens of concern, and then design the system accordingly. Yeah, so you would see that in this case a dose of 12 millijoule would be sufficient already for a geometric mean target of 200 fecal coliforms, and in the right example, you would need a lot higher dose. So you can account for the specific properties of your water by these modern design approaches. And all this is also today guided on how to do this by a number of guidelines. And I would like to predominantly talk about this one, because this is kind of the most extensive UV disinfection guidance manual, which gives a lot of guidance on how to conduct validation testing in order to verify the true performance of a UV system. And this NWRI guideline has been specifically developed for water reuse in the US in order to comply to the most stringent guideline of the California Title 22 requirements, which are asking for a total coliform count of only 2.2 total. And this UV disinfection guidance manual actually was predominantly developed for drinking water applications. So when this concern about Cryptosporidium and Giardia came up, and the notice that chlorine is ineffective to those pathogens, that was developed, and it is the way it is written, it's so flexible and gives so much guidance that it's also well applicable to wastewater. And that is, for instance, done also by the Australian Class A recycled water guideline from Victoria in Australia, or by the IUVA guideline for secondary wastewater effluent design. So they all base now on the procedures described in this drinking water manual, and we were actually the first ones validating our systems already against that close to 10 years ago. And we are still continuing doing this. And a validation actually works that way, that you have a water sample and you determine via this collimated beam apparatus how the dose response behavior of these challenge microbes is. So by that you get such a curve, here this curve. And then you use the same challenge microbes, spike them into your reactor under controlled conditions in terms of flow rate, UV transmittance, and so on and so forth. And you determine what is the log reduction. And then from the log reduction, you go to this dose response curve. And then, I think the water is in front of my pointer. And then you can determine the UV dose. And in this way, it's not a uniform dose anymore, but it's called a reduction equivalent dose. That means it's always related to a certain reduction achieved with this specific organism. Yeah, so this is also a change in understanding. There is not only a dose of 20 or 30 or 40 or whatever, but you always, in order to understand what that means in terms of log reduction, you need to tie it to a certain organism and their dose response behavior, because that's the way how it was established. And so in order to understand how well a system is really performing, it is good if you test it under most varied conditions. And that is what we did, for instance, with our latest open channel wastewater product. We tested it over close to a year under very varied conditions according to all of the protocols which I showed you previously. And as we did cover a wide variety of flow rates, UV transmittances, and surrogates, which all have a different dose response characteristic, we now can use the results which are aggregated in such a complex validation formula in order to properly size the system according to your specific waters. Well, all we need is to take a water sample in order to determine how sensitive your pathogens are. And then you can enter this as the DL value, so this is describing the UV sensitivity. And you will exactly know under which conditions the system will you provide a log reduction of 3, 4, or whatever you need. And in order to allow later on a safe operation in line with the disinfection results, we are collecting sensor readings. There is a sensor in each of the banks in order to monitor the level of intensity which is delivered by the system. And that is later on the parameter which is used to control the system in a way that it's always delivering the performance required. This is actually the procedure on how you can determine the site-specific conditions. So you take a water sample from the site, determine the specific dose-response behavior, enter it into the validation formula, and then you can design the system accordingly. And this dose formula is also used for the control of the system. Now, before concluding, I would also like to talk a little bit about photoreactivation. Yes, it happens because this is a natural process of the organisms which are exposed to sunlight and which need to have some repair mechanisms. And it actually happens for both low pressure and medium pressure systems, as you see here. So the white bars are for low pressure, the gray ones for medium pressure. But if you look at the dose levels, yeah, you only can observe it probably up to a dose of 10. Then after that, it's really more or less close to 0. So that means that at typical design dose levels we apply for our UV system designs, you don't have this effect anymore. And this has also been proven by another study which has been conducted, where you see here you can lose about 2 of your log-in activation if you only apply a dose of 8 millijoules. But if you go to a dose of 40 millijoules, then it's more or less 0. Yeah, so there cannot be any photoreactivation considered. And I think also during this real-life tests, yeah, we also know that there is no photoreactivation observed. Yeah, this is about control strategies, but as I need to close, I will only highlight that these are all parameters which are impacting today's dose. And in order to safely operate at the most beneficial economics, it's important to consider all of these yellow-marked parameters, yeah, because then you can ideally operate your UV system. So let's... Yeah, and especially since UV systems are typically designed for worst-case scenarios, yeah, taking end-of-life conditions, most foul conditions, it's so important that you monitor all this and that there is an intelligent control which modern UV systems have, and which are having a closed-loop control to adjust lamp output, to bring in banks in operation or lamps in operation or discontinue them just in response to all of these parameters. And therefore, by such an intelligent control, you can have performance compliance and generate OPEX savings. And there's, for instance, an example from the US where we have a system installed more than 10 years ago, and where we applied this new dosing control philosophy, and then the operators were quite happy because they could save a whole lot of money because of changes to this intelligent control. So therefore, I would like to conclude that that UV is really a true alternative to chlorine, and that there are guidelines by now established which assure a safe system design, which give you the reliability you want to have, that the performance is okay, and that photoreactivation is taken into account when designing the UV system for appropriate dose levels, and that sophisticated control algorithms allow you proper performance monitoring and assurance, as well as reduced operational costs. So I'm open for a number of questions, and otherwise you can also address me via email, and I would be happy to answer.